Hello everyone, my name is Ferri. Today I'll be sharing with you my work on crowd modeling for stadium design. I've been working as the lead student on this project to develop various human behavior parameters for stadium design, accompanied with Timothy Young, who has been advising on computational egress modeling, and with the supervision of Dr. John Gales at York University in Toronto, Canada. First, I'd like to start by discussing why the study looks at stadium design and why it is of unique importance. This is not only because stadia accommodate extremely large crowds, commonly in the tens of thousands of people, but more so because they must accommodate for the mass ingress and egress of these crowds within short periods of time. This possesses unique problems and credible areas of concern regarding the safety and accessibility that is available for diverse crowds of people that we see at stadium events. This video was taken from one of our studies where you can see that a lady dressed in green and black has waited for the majority of spectators to evacuate the stands before she feels comfortable to leave with a child. Although this has permitted a clear and free-flowing pathway, you can see that it still takes her a considerable amount of time. She, with her child, represent one of the many movement profiles we have observed that present with more complex behavioral profiles and that are outliers of the so-called average population, and are therefore significantly impacted by designs that are not accommodating to their needs. A method that we use to evaluate accessibility in stadia and analyze the way people use the space is through crowd simulation software. This is a tool that is available for practitioners to analyze crowd dynamics and human behavior. It can be used to simulate models for regular circulation, ingress, egress, evacuations, emergency situations, all of which is an important tool in the process of validating designs for safe, usable space. Using this tool, behavioral profiles are commonly described by the social force model and are dependent on industry standard metrics and/or project-specific data input. These, however, pose limitations on the functions and outputs of crowd simulation models. This is because industry standard metrics are not authentic to the population at hand, but rather use a generic distribution to describe the agents. Freund distribution, for example, is a commonly used metric, the one in which is discussed in the study here today, that assigns speeds based on the density of crowds, which is based on studies produced nearly 50 years ago. So where project-specific data has the ability to overcome these limitations and better reflect the crowd at hand, they lack diversity and movement representation and are relatively unavailable to use in practice. Looking at these limitations, we pose the following questions. How accurate are crowd modeling methods and computational modeling tools for stadium designs? How can we increase the reliability of their functions and outputs for practitioners to use? So to address these questions, we look at the stadium you see here. This is a tennis stadium that's located in York University. It was built in 2004 and has a capacity of 12,500. So since 2017, my team and I have been conducting studies at an annual 7-day international tennis tournament that takes place here. Choosing to model the stadium allowed me to build upon these studies. More specifically, I was able to acquire project-specific data to authenticate the models I am presenting here today. The objective of the study is to therefore configure 4 comparative crowd simulation models to analyze the impact of authenticating models with project-specific data as opposed to relying on industry standard metrics. So in order to do so, we use this event to analyze the crowd and establish a set of agent profiles and demographic distributions. The models are all built to simulate the same evacuation. They only differ in terms of these 2 characteristics. So profile parameters are what describe the agent profiles. This is largely dependent on the speed and the radius, which is half the distance from shoulder to shoulder, as well as the demographic distribution, which is what assigns how many of each agent profile is then present in the crowd. To start, this table outlines the profile parameters by speed and radius that were used in the study. The default profile represents that which was preset by the software based on industry standard metrics. In this case, it adopts the Freund commuter profile and distribution. whereas the remaining profiles were adapted from previous studies I conducted at the stadium. This data was developed for the SFP Foundation on Movement and Anthropometric Studies. Walking speeds were established for the variety of demographics you see here, placing particular focus on persons with mobility impairments. The radius data, however, has not yet been established nor readily available. Therefore, I analyzed the crowd demographics again to develop these preliminary measurements for this study. The able-bodied profiles are divided into age groups for average profiles that are not inclusive of more complex demographics and movement abilities that we'll see in the following profiles. Mobility limiting impairments describe cases that result from psychological or physiological abnormalities. Overweight and obese profiles are once again divided into age groups, and other mobility limiting profiles describe the mobility restraining conditions that are not a result of a physical impairment. Using these agent profiles, this table shows the demographic distributions that were then configured for each model. The total population for all models was set to 6,250 people, which is half the capacity of the stadium. And before moving forward to the models, it is important to note that using these profiles, all models speak to standard egress scenarios with low motivation principles, meaning that they are not reflective of emergency evacuations. Moreover, these models are not for validation purposes, but rather they have been designed to illustrate the impacts of including project-specific data. Model 1 is representative of the current state of most modeling applications when relying on industry standard metrics. So it does not have any project-specific data for agent profiles nor demographic distributions. And instead, this model uses the default setting that's provided by the software, which in this case is the Ferri commuter and distribution. Like Model 1, Model 2 assumes that all people are capable of being represented by an average profile, and then disregards any of the more complex behaviors and profiles. This model then uses the project-specific data for able-bodied profiles only, and the demographic distributions were assigned based on the observed presence of each of these populations at the event. Model 3 is the most authentic and sophisticated version of the set because it was configured to reflect the observed population at the event as accurately as possible. Profile parameters were manually inputted for the more complex profiles, including mobility limiting impairments, overweight and obese profiles, and other mobility limiting profiles based on their observed presence at the event. These proportions of profiles were then subtracted from the respective able-bodied profiles to configure the model you see here. Lastly, with Model 4, it was constructed as an additional piece to give insight to fully inclusive designs. Otherwise known as universal designs, these are environments that are optimized to meet the needs of all people. And in this case, it would be an environment that is fully accessible and offers equal service, availability, and opportunity for all people independent of any mobility limitations. So essentially, it would be a stadium that enables someone with a cane, for example, the same freedoms, accessibility, and safety as someone whose mobility is not defined by the use of a mobility aid. All the same agent profiles that we saw in Model 3 were used in this model as well. The only difference is that the demographic distributions are not reflective of observed population at the event, but are rather defined by a variety of demographic statistics provided by Statistics Canada. So the major defining parameters used to describe this model include that 63% of Canadians over the age of 18 are overweight and obese. In addition to this, it was found that 9.6% of Canadians over the age of 15 have mobility-related impairments. Each model was then simulated 10 times to record the amount of people egressed with time for each simulation. I then took the mean results to produce the graph and table you see here. It is important to note, however, that these models are in the introductory phases and are subject to modifications. So the outputs presented here are preliminary findings. Model 1, representing the use of industry standard metrics, underrates the amount of time for the population to evacuate by showing the fastest egress, whereas the total egress gradually slows down within the next models. Model 1 and Model 2 possess a similar trend in their egress with a small variation in time. This is not unusual because the average speeds presented by the able-bodied profiles are relatively within the range of the Ferri commuter. So in comparison, after the first 3 minutes of simulations, these two model outputs vary by about 6%. Model 3 shows an even slower overall egress, along with unique pedestrian behaviors, based mainly on the fact that the newly introduced speed parameters are all slower and the radii are greater. It is the most authentic and reflective model, considering it's based on real observations of the stadium crowds. So it is an improvement on models 1 and 2 because it includes this diverse set of profiles that is inclusive of more complex profiles, instead of being limited to distribution curves and average populations. Comparing the accuracy of outputs at about 3 minutes to that of Model 1, we see a deviation of about 17%. This model shows the increasing impact that project-specific data has on the functions of crowd simulation tools and highlights some limitations of relying on industry standard metrics. Lastly, with Model 4, we recall that we aligned the crowd demographics with those of the Canadian population to simulate a theoretical crowd that echoes the ideal diversity that inclusive designs aim to achieve. With this in mind, we note that this model shows the slowest overall egress, due to the increased proportions of more complex profiles having slower speeds and greater radii. Comparing the accuracy of outputs at about 3 minutes to that of Model 1, we see a deviation of about 23%. This model brings light to the impacts of increasing the proportions of profiles with reduced mobility and works towards highlighting interest points for a design to better accommodate for diverse crowds. It is important to note that although the study presents ways to overcome some limitations of crowd modeling tools, additional research is still required to develop these tools further. Notably, the presence of complex profiles is limited to those that were presented in Model 3 and 4, whereas there are many more profiles that would impact the functions and outputs of these models. So this would include other impairments that may be a result of psychological and physiological abnormalities, such as cognitive deficiencies or mental health disorders, vision impairments, and so forth, which would also be impacted by things such as intoxication and mobile phone usage and so forth. So unfortunately, we could not include all of these many types of profiles, partly due to the lack of movement data that is available and the inability of crowd simulation software to accurately incorporate these demographics. These simulations are also limited to the architectural features of this particular stadium, which consists of relatively short travel distances in comparison to other environments. So in turn, I would anticipate that increasing the inclusion of more complex profiles, as well as the crowd size and travel distance, would all contribute to increased egress times and different trends in human behavior. The current findings presented today highlight the limitations of relying on industry standard metrics in comparison to increasingly authenticated models that incorporate project-specific details on the observed population. These models bring attention to the prevalence of varying movement abilities and how excluding them can lead to inaccurate results. These profiles must therefore be included in modeling methods to accurately depict the population at hand and work towards creating inclusive designs. For additional confidence, we are working to validate these models against observed egress scenarios and compare them with a range of crowd modeling software. So in addition to the overall evacuation performance that was presented today, the egress trends of each group demographic are being independently analyzed to give further detail to the crowd behavior. Future research should also expand upon the degree of accessibility movement considerations, such as to diversify available data sets to the inclusion of profiles with psychological abnormalities, other physiological abnormalities, intoxication, mobile usage, and so forth. Now, I would like to thank you all for listening to my presentation, and thank you to Thunderhead Engineering for hosting this conference and having me here today. Along with the members of our research team at York University, I would like to thank the Human Behavior and Evacuation Skills team at ARUP and the Accessible Environments team at ARUP, as well as Lund University and the SFP Foundation for together making this study possible. Thank you.
Okay, welcome over from the talk. We have Julia and John here to answer any questions you might have about the presentation. I mentioned, thanks Dave, Stacy, for the comment about the data set. I think a lot of people get a lot of use out of this. And maybe if you could both, maybe John or Julia either, mention sort of some of the work that's been going on to develop this demographic data
for the SFP project.
Mm-hmm.
Yeah, I'll just give a quick overview of that and then pass it to Julia to go more specific into this project. So the SFP has, along with York University, our collaborators at ARUP, and with Lund University as well, to look at movement in general. We've been mostly looking at movement speeds and modernizing these, looking at a whole wide range of different infrastructure types. So what you've just seen was the Aviva Stadium, or York University Stadium. But we've also been looking at intercity commuter railway stations, as well as airports, which are currently being derived right now for new speeds for those. The cultural centers that you saw yesterday, even old age homes. So a wide range of movement speeds. And the nice part of the SFP Foundation support was that this enabled us to really accelerate the generation of these movement speeds, to give people like Julia an opportunity to work on these projects. And any time that you're trying to do this takes a long period of time to go through, which I think Julia can elaborate a little bit more specifically about the stadium ones. But in general, that's kind of the support. And with the continued support, not to keep the conversation going too much longer, we're using a bit of this to branch into in Canada, in Quebec specifically, to try to create educational materials for human behavior in fire situations in the French language that can be used in that province. So it's a far-reaching foundation project, which has been great.
Excellent. And it's my understanding that through the work with the SFP Foundation, that the data sets will be made available through some web portal or some access eventually as well.
Exactly that. So there's a database that is being created that can be accessed, and then you can basically search the infrastructure type or whichever. It's still being finalized. There's still a lot of work. A lot of the basis, though, is based on Steve and Karen's previous work with the handbook, but more putting it in a way that you can integrate it easily computationally within your models, rather than needing to lift that massive book and trying to find each thing.
Yeah, no, that's fantastic. Julia, there's a question here about stadium. So are the stadium attendees typically representative of the greater population, or do you see sort of a subset of the population there?
Yeah, so we have actually studied a few different stadium, and so this one being actually a tennis stadium, you do see a particular crowd that would potentially be different than a crowd that you might see at a soccer stadium or like an American football stadium, as well as a baseball stadium. So we're actually looking at how those different populations will differ. And here being a tennis tournament, we do see a crowd that is much more diverse. So we do see a lot of families, we do see younger kids, as well as a lot of seniors. Whereas potentially if you're going to, let's say, like an American football game, you see a lot more of just youth and adult, and you'll see less of seniors. So in this particular study, I would definitely say that it is more representative of the diverse populations that we do have in the greater population, of course. But that is why I was putting that last model out there, to kind of give insight to, hopefully if we're able to move towards offering more accommodating stadiums, then we're able to encourage a more diverse crowd to be able to attend, if that makes sense.
Yeah, excellent. And then how did you physically collect the data in the stadium?
So the majority of the data was collected with all different video cameras that were strategically placed at different parts throughout the stadium. So we looked at a few different occurrences on just flat ground outside, how people were moving through unimpeded ground, as well as stair movement. So this was collected with video, and then afterwards we would analyze that. As well, some stuff was followed up with surveying and actually speaking to some of the groups that were there as well.
Great. There's a comment here about the effect of beverages with 5 to 6% alcohol. Is that effect on mobility considered? Which is very normally served with, like, in cricket stadiums, and especially anything in the US with baseball or football or anything, the impact of that potentially on the movement.
So that wasn't incorporated in this particular study, but it is something that we're considering, and we do acknowledge that it does need to be further studied for this study as well as future ones. We are looking at the effects of intoxication, and especially because at stadium events, yes, I think all around the world it is very common to have I guess you can say a degree of intoxication with different populations there. So it is something definitely that we would like to consider and move forward with doing, but this study does not incorporate that, no.
Yeah, I saw a tweet the other day with somebody who had just recently published a study on the effect of that on movement speed, and I made a comment with well, how are we going to, where should we put this in the agent profile, the intoxicant level, and then, some emojis of like beer and wine and then barfing or something. So yeah, I think that'll be interesting to see how that incorporating those characteristics.
As a thing to add to that, in the first year that we were filming the stadium, we had cameras around, and 2 individuals who decided to get rowdy were filmed, and the police knew that we were taping at the stadium, and they're like, well, can we have access to your tapes to see how much they were drinking beforehand? And it's, but we, as Julia said, we are, that is another part of this work that we're beginning to look at, but it's highly complicated with ethical considerations and things.
Sure. There's a question here about what software did you use to model the project with your input data?
So this study was done using Mass Motion. It was not, how do I say, we did find that trying with other softwares as well, it's, I don't know, John, if you would like to actually expand on this.
Yeah, I don't think the point of this particular presentation is which software. It's more of the speeds that, like, you could use a different software and still potentially see the same goal of what we were trying to show, is that the demographics are going to change the speeds in some cases quite considerably. So
yeah, so I suppose any tool that had some demographic ability where you could put in the speeds and everything, like any tool could be applied here,
or at least show a difference in the things. The cultural center was more about looking at different types of softwares and such.
Somebody here is interested in where the walking speeds for different age groups, where those come from. They were not expecting to see high values up to 2.85 meters per second. Say they're working with age-related speeds and that do not exceed maximum of 2 meters per second for young and fit adults. So just had a question about those, the higher end values.
So these were taken from the previous studies that we did conduct here at this exact stadium. And those were taken for unimpeded movements on flat horizontal grounds that were just outside the stadium. It is, though, still important to acknowledge that, like I said earlier, these are kind of preliminary results. So we are still kind of weeding through a few of these things and still looking at a couple potential outliers and whatnot, and reevaluating those data sets and how they are being incorporated into this. I do see that there were a couple that were on the higher range of walking speed. So those particular ones, I am going back through the footage to see further detail into what that particular case was. But they, like I said, were all taken from this exact study over the past 3 years of footage that we had there.
Okay, and there's a question about pre-evacuation time, like we saw with the lady with the children in the video. Was that taken into consideration for the simulation?
So all the models were actually given the exact same pre-movement data, and this was taken from a previous study from somebody else that was on our team, which was also done at a stadium. So just generally speaking, it was a mean pre-movement time of about 36 seconds with a standard deviation of about 19 seconds with a a normal distribution. So it was kept consistent across all 4 of the models. In this particular study, that wasn't really the focus of it. So theoretically speaking, for this study, it would not have mattered even if we left it as a 0 pre-movement time, because we just really want to look into the different effects of having and changing the profile parameters and the demographic distributions. So that's why we kept it consistent.
Great, great. And then were there any notable differences in speeds and demographics between the years that you gathered data? Any like year-to-year changes that were noticed?
No, I wouldn't say. I'm trying to think if I really have any good comments on that, but I don't really recall actually seeing any particular differences, except for every year, this particular event, it alternates between the men's and the women's tennis tournaments. So I would say that maybe to a degree, the change slightly, or actually more so with the alternating years that it was the men's tennis tournaments, it was a larger crowd. So there was more people present, but not any more populations that were more prevalent than others.
Yeah, just to add to that is the tennis associations in Canada are very particular about season tickets. So a lot of the people who are attending this would have purchased day passes 2 years before the event. So there is some consistency between the ticket sales of who's attending each year.
Oh, that's interesting. Okay, that's a good factor to consider. That's good. I don't see any other questions now. I'm just looking here in any other channels. I don't see anything. So I think with that, we'll wrap this up. So thank you very much for the talk. Thank you for the Q&A session to both of you, and all the good work you're doing. We look forward to, future releases of this information and the results of your work.
All right. Thank you very much for having us.
Yep. Thank you.
Yep. Take care. Bye-bye.